Okay, we're back to soils. Where do they come from? All that weathering, the chemical, the physical, the biological processes are breaking down minerals, which break down rocks. The more water in that environment, there's going to be more chemical weathering, more more higher temperature, there's going to be more chemical weathering. The more activity, life activity, is going to create a more acidic environment. So wet, warm, um, lots of biological activity. Places like the jungle or rainforest are going to have more chemical weathering than, say, a cold, dry place like a cold desert. There's a short video, check that out. It's like 8 minutes, maybe a little bit more, on soils. All right, soils are typically described as being in these layers called horizons. So a layer, a layer of soil is a horizon, and then a sequence of soils for a certain area is called a profile. So they develop in horizons and they are in a soil profile like this. There is inorganic material, which is the decomposed rock, and then organic material that can be alive or decomposing dead stuff. So the general layers starts at the bottom with rock, and then there'll be ABC. So C is next to the bedrock, and so going to mostly look the most like what the original rock was. And then there's B, and there's A, and then there is the O horizon, which is a horizon rich in organic material. Let's look at each of those layers separately here. There are a bunch of different horizons. I'm just going over 1, 2, 3, 4, 4 really horizons here, but there are many, many more. We're just going to go over the general classes of horizons. O has mostly plant litter and other organic material. This is what we think of as the topsoil. The A horizon does have organic and inorganic, and it's what's called the zone of leaching. So rainwater is going to hit that A layer, and anything in that layer that is soluble is going to be washed down to B. The B horizon is the zone of accumulation. And C is again that partially weathered bedrock, and R is the rock. There are different kinds of B horizons. Here's examples of those. Argillic B is going to be an horizon where it's collected soil, clay from up above, so clay has washed down. So a really clay-rich horizon is called an argillic horizon. B sub K is a horizon where calcium carbonate has dissolved and come down to the B horizon. If there's a lot of that calcium carbonate coming down, it's called a caliche soil, and caliche soils can be kind of rigid, almost lithified, but not really. But all the pore space will be full of calcium carbonate. The United Nations has 110 different soils on its map. The United States has 12,000 different classifications of soils. I've only given you like 3 B horizons. This is a map from the USDA of soil horizons. So you can take a look at that. Click on this link for the soil map and you can find a map from the USDA and also see a link here from the USDA of different soil types. So a map and the different types. Another special kind of soil is lateritic soils. Are also called oxosoils, and these are the soils that occur in the rainforest. They are areas where there's really high temperature and lots of rainfall. Because of all that rainfall and high temperature, the soil is heavily leached. It's so leached the quartz may even dissolve. What's left behind is the insoluble contents near the top, which are things like iron and aluminum. Metals are left in the soil. That makes the topsoil not very fertile for farmland. The soil is too leached of its good stuff. all the nutrients are washed away by acidic rainwater infiltrating that soil. You may know, like a rainforest, the nutrients are held in the canopy. The forest holds the nutrients, not the soil, because it's been washed away. One thing that, and once it, like a tree dies in the forest, it's very quickly decomposed by decomposers on the forest floor. The way the bad thing about this is when people try to live in these areas and they're trying to do farming, they do slash and burn farming. But that's only going to work for a few growing seasons because there's no nutrients in the soil. The slashing and burning is only going to last a few crops before the soil gets baked and the soil hardens into almost like bricks. The metallic soils there are going to be soils that are really rich in kaolinite, that's clay, goethite, hematite, and gibbsite. Those are different rocks that have iron and aluminum in them. One of the primary resources from regions that have this kind of soil is bauxite, which is aluminum oxide. Bauxite is an ore of aluminum, and it forms like coal does. So if you know anything about coal, it forms in layers in sedimentary rocks. So bauxite forms in layers in soil. So in order to get that resource bauxite, they do strip mining. They'll remove whole mountains. It's like mountaintop removal just to get to the layer of bauxite. The top mining countries for bauxite are those that have the right climate. So Australia, China, Brazil, India, Guinea, Jamaica. The United States has no real places where there's bauxite. Okay, so it can be really messy way to mine. The key to that is recycle because bauxite is used in like beer cans, right? It's aluminum. So that's why we should all recycle our aluminum. All right. Soil is described in different ways. We can look at the color, whether it's rich in organics, it can be black and brown or gray and white if it's really leached, or red and yellow if the layers are oxidized. You can see in this image here lots of different colors in the soil horizons. And then there's texture. So a texture of a soil, if you pick it up and rub it in your hands, it may like, you could maybe make it clump in your hands, it'd be rich in clay, maybe it feels gritty, it's got sand in it. The way a soil scientist describes that sand is a percent of each: sand, silt, and clay. How well it clumps, like squeezing it, really tells the structure and the moisture content of that soil. Some important ways to look at soil would be its soil fertility, and there are places in the world where there's more fertile soils than not. But we're looking at where we can grow food. So the three main limiting factors are nitrogen, phosphorus, and potassium. So if you buy a bag of fertilizer, it'll have the nitrogen value, the phosphorus value, and the potassium value. And the availability of those different nutrients is going to depend on the climate, what is the parent rock that eroded to form that soil, and what is the land use. The areas of the world with the most fertile soils are those that are kind of disturbed. So a floodplain that gets renewed nutrients when a river floods and leaves its channel, maybe along the flanks of volcanoes, and places that have had forest fires where you're creating raw new nutrients. Water content. So this is about the moisture of the soil. Soils can be really wet or really dry. So on the left here is a picture of a swamp. That soil obviously is wet. It's wet probably year-round. Depending on where the water table is, maybe some of that soil is exposed from time to time, but it's wet. On the right is a desert environment where the soil can be very, very dry. So the moisture level relates to the stability of the soil. So a swampy soil like this, where there's flat topography, that's really stable. In an area like this in the desert where the wind can blow, and erode the topsoil away, it can be really fragile. All right, erosion rates. This is one thing that we study in geology, and we look at it in terms of the volume of soil eroding over what amount of time, over what surface area. How much soil moves during a certain amount of time over a certain amount of ground. And how do we measure that? Well, geologists have been coming up with different ways for forever. So how to measure it? You can look at the amount of sediment load that's in a stream. So a watershed is going to have erosion, transportation of sediments, and then it's going to get into that watershed feeds down to a stream. You can measure the sediment in that stream and weigh it and see how much erodes from that watershed. That happened a lot with the water supply here at Appalachian State University. Our water supply is in a valley. It was deforested and there was lots of erosion, lots of sediment coming into our reservoir. They've let the trees grow up in that reservoir and now there's way less sediment. They're measuring way less sediment these days coming into our reservoir. It can be measured directly from a slope. So you can measure the slope with a fancy surveying equipment and then come back years later and measure it again and like get that surface plotted, get the new surface plotted, subtract those surfaces and figure out the volume. This reservoir bit, you can measure the storage capability of a reservoir and then see if that volume changes over time and maybe it's filling up with sediment. So there are ways to measure soil erosion. Here is what's called an alluvial fan. An alluvial fan is a feature that forms in basins like this. So when these mountains erode, this volume of sediment is coming out of the mountains and you can measure the volume of that alluvial fan as well. So here's some scientists doing those measurements, measuring rainfall on a surface, maybe simulating that rainfall. Here is surveying equipment on a slope. Here is measuring what happens on crops and rain amounts and how much erosion is happening with different crop cover. And then they come together, the 3 scientists or 4 scientists, and they would put their data on a map. And that map would tell, and it's usually going to be in a GIS format these days. And then that they can compare these rates over time and maybe land use over time and crop cover over time. So that would be a collaborative effort to quantify that information for that valley. Okay. Sediment pollution, not just the pollution of sediment, but the sediment itself being a pollutant. Look at this field. This is sediment pollution. So whatever that is, I don't know what plant that is, beans, strawberries. Water is washing off of those plants and all this sediment that's exposed here, this soil is washing down into a creek. It chokes streams, it fills lakes, reservoirs, ponds, canals, ditches, harbors, pollutes the ocean. And then it can bury vegetation. So here, maybe these ends of these crops are getting washed away by the water, and that sediment is going to go somewhere else and maybe bury other vegetation. It's also depleting the soil in that field. So that field is getting harmed by losing that precious topsoil. And that could be infertile soil, some of it, that then washes over top of other fertile soil and then down maybe into a reservoir that's losing its storage capability. So that erosion is bad. And it gets into, it gets into our waterways, and that's never good for the aquatic organisms. Okay, what causes all that erosion? So construction is probably the worst. Houses, highways, whatever it is, you're exposing that soil. So here is, they pretend, right? Here's that black plastic that is put at every construction site to capture the soil. But here it's failed and nobody fixes it. They do it just to get the permit. And then there's no grass on this lawn, so just getting gullied and gullied and gullied, and sediment's going to wash down to the stream. Construction is just as bad as farming and agriculture, whether it's pigs or strawberries. There's also deforestation that could be human-induced or not. So forest fires happen naturally all the time, or maybe it's from clear cutting. And then channelization of streams. So any kind of flood control measures could lead to soil erosion. How do we stabilize that? Contour plowing is one. So these swoops here are like contour lines along the topography of that hill slope. Wind fences, putting up a literal fence or even a row of trees to stop the wind-blown erosion. Dams and ponds to hold sediment and hold runoff and trap sediment. This happens a lot out west. They'll have a catchment pond for heavy rains, and then they'll let some of the soil settle out. And then also just always planting vegetation just to halt the movement of the topsoil. Humans change the landscape by changing land use. So we're clear cutting, so it was a forest, and we're clear cutting it. One of the worst parts they found of clear cutting is the interconnectedness of trails and roads, because they truly become like riverbeds. And if you've hiked off the parkway or any state park in this area, the trails become little rivers. And so a lot of trail maintenance is putting in like water bars horizontally across a trail to divert water so it's not just becoming like the river on a trail. Farmland is really similar to clear cutting as well. So always adding trees. When you add a tree, looking for a plant, I don't have one. A tree, the rain is going to be intercepted by the leaves of that tree. So instead of pounding rain, water hits the tree and then is going to flow down the trunk of that tree. Trees also draw water up through their roots and return that water into the atmosphere through transpiration. All right, urbanization. Urbanization really involves adding impervious surfaces. That is, surfaces where the water can no longer infiltrate through the soil to become part of the groundwater supply. It stops on that impervious surface, whether it is a building, a parking lot, a sidewalk, whatever it is, any pavement. So that is probably the worst part of urbanization. During construction, there is a large pulse of sediment to the streams. Over time, the streams are going to then lose their volume, that stream channel. As the channel fills with sediment, the water gets displaced, and then that is going to increase the magnitude and frequency of flooding. We see that on campus with Boone Creek. One thing that we do during construction is scraping off soils and preserving it somewhere in a pile, maybe putting a tarp over it. But when that happens, the soil loses its strength. It loses that soil profile, those horizontal layering. So when it's put back in place, it's not the same. It's not the same soil.